Hi, I'm Ben-Yaakov. This presentation is entitled Mutual Inductance versus Transformer, the Power Electronics Perspective. Here I will discuss the structure of multi-windings on a core, how to model them, the issue of simulation, leakage inductance and how you model it and calculate it, a few words about capacitances, and finally how you measure the parameters of these models and elements. In many applications in power electronics, we need an element in which there is a number of windings. In this case, I'm showing two windings on a core, and they can operate as a transformer, like in a bridge converter, PWM converter, in a flyback. In this case, we'll need a gap in order to enable energy storage within the core. Forward converters, coupled inductors, again, we'll probably need a gap, or use a powder iron core in which a ferromagnetic material is mixed with some inert material in order to lower the permeability and thereby allow storage of energy. Another possibility is to use the wound core, which are ribbons wound. They are material that have high conductance, and therefore you have to form them in thin layers so the eddy current will not cause heavy losses, and then you can wind on them the windings. In all cases, we have a number of windings in here. I'm showing two on a core, and it is important to realize that we have two types of magnetic fluxes. There is one common flux that is going through the core, and then there is a stray flux at the primary and at the secondary, sort of escaping from the common flux. These are called the stray fluxes, and they are the reason for the leakage inductances that we'll talk about. A measure of how much of this flux is actually running away is the coupling coefficient, which is given here, which can be expressed as the ratio of the common flux over the common flux plus the stray flux. Say this would be for the primary. So when K is 1, this means that all the flux is common and there is no stray flux, while if K is much less than 1, then an appreciable part of the flux is actually running away, which is in many cases causing a lot of trouble. There are two modeling approaches for these multi-winding wound on a common core. There is the mutual inductance representation. This approach is used in many physics books and also in electronic circuit book or network books, and it's based on a concept of mutual inductance between two inductances. So we have two inductances, L1 and L2, which are coupled by this mutual inductance, and we'll elaborate on it in a while. Another approach is the transformer approach, in which we have an ideal transformer with, say, a certain turns ratio, and I'll talk about this a little bit later too. But here we see the leakage inductance, we see the primary inductance, we can also reflect it at the secondary. Here I'm showing it at the primary side, and we have also in this case the leakage at the secondary side. We can also transfer it to the primary. We'll talk about it. So these are two different approaches which are used, and let me talk about first the mutual inductance approach. Here we have an element in which here is the Laplace transform representation with two impedances, SL1 and SL2, and there is another common impedance, SM. And the meaning of this mutual inductance is that there is some voltage imposed from the primary onto the secondary and vice versa that we can represent here by voltage dependent sources. These are voltage sources which are dependent on current. So this one here is a voltage source depending on the current at the secondary. That is, here is the current at the secondary, and the value or the magnitude of this source is SM. This is the mutual inductance value times I2. And then exactly at the secondary you have the same thing, except of course that now this voltage source is a function of the current at the primary. Now the coupling coefficient is coming here in the expression for M. M is equal to K, the coupling coefficient, times the square root of L1 times L2. So this is the interpretation of the meaning, you might say, of this mutual inductance, these dependent sources. So how do we use them? And I'm just showing a very simple example. We have an open circuit at the secondary, we have an excitation at the primary, and I'm trying to find out the ratio between V out and V in, or calculate V out as a function of V in. So in this case, I2, that is the current here, is of course 0, so therefore there is no induced voltage here, and the current at the primary will be V in over the impedance in the Laplace form SL1, this is the current here, and therefore the output voltage, which will be only this dependent source, will be Sm times V in over SL1. This is the current of the primary. The Laplace operator is sort of divided out, and while M is the K times square root of L1, L2. So I'll plug this M into this relationship here of M, and I find that V out is K over a square root of L2 over L1, and now we know that L2 over L1 is N2 over N1, that is the turns ratio. So what I have found, which is of course should have been clear, that the voltage at the output is the turns ratio N2 over N1 times V in. But here we have some extra element which usually we neglect, we don't pay attention to. This is the coupling coefficient. If K is really 1, this is the classical transformer relationship. But if K is not 1, then this relationship has to be corrected, as a matter of fact, by this coupling coefficient, because not all of the flux generated by the primary is coupled to the secondary. So this is how we use this model of mutual inductance. Now there are some problems with this representation, and therefore power electronics engineers don't like it very much. Number one, it's rather complicated to analyze. It has dependent sources, it depends on the current on one side and the other side, and it turns out that it's really a mess to write out the equation of the circuit. Also, it's non-intuitive. You really don't see many elements that you really like to see. For example, the leakage inductance. It's sort of hiding inside this mutual inductance with the K coefficient, with the coupling coefficient. You don't see it at all, and you don't see how it interacts with some other elements like capacitor and causing some parasitic resonance. You just don't see it. This is why power electronic engineers really like this representation. Here we have a clear information of what we really like to see. We have the leakage here, which is equal to L1. This is the total inductance of the primary times 1 minus K, K being the coupling coefficient. What is remaining here is L1 times K. We have at the secondary the same thing, L2 over 1 minus K and K times L2. And in between, we do have an ideal transformer. This transformer really doesn't have any characteristic of impedances that you are interested in. We just serve to do the transformation between voltages and current like an ideal transformer. So we'd like to make these impedances, that is the inductance of this ideal transformer, to be very large. And of course you use K equal to 1 because now this is an ideal transformer. The transformer is this thing altogether. This is just the heart of this transformation between current and voltages. Now we can do reflection between primary and secondary. We can reflect the input to the output, etc. And the rules for reflections are that when you have an impedance at the secondary side, it's 1 to n turns ratio, then the impedance you see here is 1 over n squared times z, And here, if you look at the secondary, there is the impedance here, then you see n squared times z. So therefore you can move this leakage inductance to the secondary if you wish, or you can move this inductance to the secondary if you wish. It really doesn't matter as far as the operation of this circuit goes. Sometimes it's more easier to see what is going on when the impedances or the inductances are on one side or the other. Let me move to the area of simulation. Now, many times, of course, we would like to simulate a circuit like a power converter in which we have a coupled windings on a core. And there are, of course, the two ways to go, the mutual inductance or the transformer representation. It's very important to realize that electronic circuit simulators have only the mutual inductance, M, as an element that is recognized by the simulator because it is a basic element of circuit analysis. A transformer has to be formed by sort of a sub-circuit and an equivalent circuit, and it's not inherent in the simulator core. Now, sometimes the manufacturer will do it for you, but many times you do have to do it yourself. So, in simulation, we can use the mutual inductance, which is a basic part of the simulator without no problem. Of course, we have to know what is L1 and 2 and K, or if we know M, L1 and K, because all these three are, of course, connected together. Once we know them, then we can give these parameters to the simulator and it will run. But if we like to use the transformer representation, then we need L1 or L2, we need the turns ratio, we need information about the leakage inductances, either lumped or one side or the two sides, and we have to implement an ideal transformer. Now, these two, of course, are connected by these equations that I've already talked about. M is K square root of L1 L2, N is square root of L2 over L1. The leakage is 1 minus K times the inductance, and the residual inductance, this is after we have chopped off the leakage, is K over L1 and K over L2. So how do we go about building an ideal transformer that we need for the simulator? That is, in the heart of this model that we have for the transformer, there is this ideal transformer. We do it with a mutual inductance because this is what the simulator understands. Only that we make it ideal as far as the transformer is concerned. So L1 and L2 are made very, very large. Of course, large is something relative. It should be much larger than the inductances in the circuit, so that the current that is flowing through these inductances L1 and N2, which are just represented the ideal transformer, the current should be low. And of course, we use M is square root of L1 L2, K is 1, because this is an ideal transformer, and N is related to L2 over L1 square root. So this will be the element of the ideal transformer, and when we implement it, we'll go back here, and we put it in here, and this will be just the complete model of the transformer that we can run in the simulator. There is another way to do it, and this is without inductors at all, just by dependent sources. So this is an ideal transformer. So this current source is dependent on the current of the primary. So if this is 1 to n relationship, then this current is 1 over n I1, and the voltage here will be 1 over n V2, the voltage of the primary. So this will be an ideal transformer, no inductances involved. There is another way to do it, just the other way around, and that is to put a current source as the primary and a voltage source as the secondary. This is dependent sources, of course. The value of this one, in this case 1 to n, will be n times I2, and the value of this source will be N times V1, V at the primary. Now, when are you going to use one option or the other? It really depends on the impedances that you have. For example, if there is an inductor here in the circuit, I'm talking about the complete converter, the complete circuit, not just the transformer, then it's not a very good idea to have an inductor in series with the current source. This could cause many conversion problems for the simulator. So in this case, you'd like to go to this representation in which there is a voltage source, which will be easier for the simulator to sort of converge into the solution. So you can use either one, and as I've said, you can build it yourself, or some vendors are actually implementing it and calling it an ideal transformer, and what it is basically dependent sources. Now let me move now to the question of leakage. Here is a E-core, as it's called. This is the common flux. These are the fluxes which are stray fluxes causing this leakage inductance. These are non-coupled fluxes. And here is a cross section. I see here this one winding, and then I see the other winding. And as it turns out, there are some theoretical expressions for the leakage. Here, this expression, which I'll go over in a second, is for this E-core, in which there are two windings. This is 1 and this is 2. They have certain width, B and B, B1 and B2. They are separated. The separation could be due to the fact that there is some insulation. If it's a high voltage on the secondary, you'd like to insulate it from the primary. Or, in fact, if you'd like to increase the leakage, you increase or put here some distance between the two. And the idea is that you allow more stray flux to sort of run away from the core. So the expression here, we have the number of turns of the primary. I should say that this is the leakage looked at the primary. That is what we see at the leakage at the primary, divided by A. A is the height of the windings, times this expression, which is C, is the separation. B1 and B2 are the width of the two windings. So this is a closed form equation from which you can estimate very accurately the leakage, and then you can actually fiddle around with this distance in order to get a higher leakage. Now, normally, you'd like to have low leakages, because in some application, or in many applications, a leakage means losses, because the energy stored in the leakage inductor is sort of getting lost to heat, unless, of course, there are some recirculating circuit, like snappers or some resonant circuitry that sort of recovers this energy. And if not, it's getting lost. So in many applications, you really would like to have this leakage be as small as possible. And in this case, you can do a bifilar winding. That is, you take the two windings and you wrap them together as if they were one wire. By this, you make the distances very small to one to the other, and you improve the mutual inductance between them, and therefore the leakage would be much lower. Another point is the capacitances. Windings have capacitances between them, and there's some interwinding capacitance between the layers. Now, these are distributed capacitances, which are very difficult to express. So usually they are represented by a lump capacitor. So this will be a parallel capacitor here and here. You can, of course, move one to the other side, reflect it to the other side. And these are the capacitors which are in between the windings. Normally, for regular circuit simulation, what is more important is this parallel capacitor. And so therefore, this would be a very standard model of a transformer in electronic circuit simulation of, say, a power converter. We have the leakage, which here is reflected to the primary. We have the primary inductance, ideal transformer, which is represented in one way or the other, and the parallel capacitor. Now note that the inductances of these ideal transformer are not supposed to interact with the circuit. This is just a conversion action, which you can, of course, emulate by dependent sources, as I've shown before. Now, how about measuring all these parameters? Well, there are really very simple procedures that you can use. Say for L1, you just use an RLC meter, open circuit at the secondary, and you measure it. Best to measure it at the frequency, which is the frequency of operation. Then L2 can be measured by RLC at the secondary. This is open. For the leakage inductance, you short out the secondary and you look up the primary, or the other way around. Now what you'll get here really a value for the leakage inductance in parallel to this primary of the real transformer. If the coupling coefficient K is close to 1, then you can neglect the effect of this parallel connection. But if K is not close to 1, then you'll have to recalculate what is the actual inductance once you know the value of this L1. And the same thing for the other side. Now it's best to do this measurement from the side which has the largest number of turns, so that you'll get a larger leakage, which is usually very small, and so you can actually measure it. Depending on the type of transformer, you measure it from the side that has the larger number of turns. And the turns ratio is, of course, very simple. If you like to measure a transformer, you put a signal generator, a voltmeter, and you just look at the ratio between the voltage from the input to the output. Again, it is better to feed the generator to the side which has the largest number of turns, so the impedance is high. Otherwise, you may overload the signal generator if the impedance of the winding is very low. And finally, how do we estimate the value of this lumped parallel capacitor? We can do it by actually a resonant circuit. Put a resistor with large resistance in series. We excite it by a signal generator. We measure the voltage here. Here we have an inductor in parallel with this capacitor, with parasitic capacitor. So as we sweep the frequency, we'll get at the frequency of resonance, and this will be parallel resonance. The voltage will be the highest. This is the value that we want, and from that frequency, we can, from the expression for frequency, we can calculate this parallel capacitor. So this actually brings me to the end of this presentation. I hope you have found it interesting and you will find it useful in the future. Thank you very much.